core, massive heavy center core and perimeter columns. As Bob described, it's got walls all the way out to the end, and it's loaded that way. Just no equations in this. I know you're all beleaguered from equations from the conference, but just some concepts, right? So on the right-hand side is the classic beam on elastic foundation type diagram. So flexible foundation, will have a very non-uniform settlement profile, but it will have a very uniform pressure profile. And conversely, a rigid foundation it's rigid, right? So it's going to settle the same, so have uniform settlement, but it will have a very non-uniform pressure distribution. And of course, on the left-hand side, Winkler springs, some thought, hey, if the loads are coming down, all the piles are the same, the individual pile springs should be the same, they'll be loaded the same, and the settlement will be the same. But it doesn't always work that way. So just a bit about, this is the iterative process and the collaborative process, right? So this is sort of Langan's and TT's approach to this project and frankly other projects as well. And I've heard sort of the common themes from some of the presentations I saw at the Congress. So column loads come obviously from structural engineer, and they could be a fixed base analysis, or in this case it was uniform springs on the piles and a load takedown. We take those loads and we apply those to our model. And determine settlements, determine piles, loads on the pile, and also bearing pressures under the raft. Calculate springs both for the piles and for the subgrade modulus. Give those back to Bob and his team. They'll run it through, I think they were using E-tabs at this point, run it through, and in some cases, the wall loads will change. So we take those new wall loads and put it back into our model and get a new settlement profile, et cetera. So we go back and forth like that. We like to think that we want to converge on wall loads. We want to see the wall loads not moving around more than a couple of %, and we want to converge on settlements and also pile loads to, I would say, typically within 10%. On this project, we were within 5%. That was sort of because of the importance of the project, we held ourselves to a bit higher standard. So this is our finite element model, the idealized profile. We model the ground, obviously, the piles as embedded beams, and the raft as a plate with its appropriate thickness and stiffness. And then apply, as I said, the loads that Bob's team gave to us on the top of the raft. So this is the first cut. This is the first one we did, 45-meter long piles uniformly throughout. And we had essentially 175 millimeters at the center, 110 millimeters at the edge. We had an angular rotation of about 1 on 900, and we thought, hey, we're doing pretty good, right? I mean, we're double, 1/2 of 1 on 500, which is sort of the rule of thumb concrete structure, right? And we thought we were doing pretty good. So we started iterating. Ours are on the top. The TT's safe model is on the bottom, and you can see that we're not iterating. We're not getting close to convergence. And in fact, on TT's model, we're starting to see reverse curvature on some of the wings. So we kind of took a step back, changed our perspective, and said, wait a minute, what's going on here? We plotted pile loads. So on this one on the left, the 0, is the center line of the tower, and then 60 is out at one of the wings. And all those dots are pile loads and pressures as well. And instead of having a uniform load from center to edge, we had much higher pile loads at the edges and much lower loads at the center. So this thing is behaving like a classic rigid foundation with uniform, trying to get uniform settlement, but having a very non-uniform distribution of the loads. So we said, all right, well, that's not working either. And I remember Bob at one point saying, wait a minute, the raft can't even handle the raft. There's no way the loads can come down and the raft can transfer it out. It's not going to happen. Well, when they started looking at their model, it wasn't happening at the raft level. It was happening probably 20, 25 stories up in the building. So at that point, the load was starting to walk out to the end walls, and we had not finished converging yet, and we had the wall loads were increased by a factor of 2.25, almost 2.5. And as Bob said, it was kind of turning into the Eiffel Tower effect, right? So all the load was coming down in the middle, but it was ending up on the edges. And that was causing a lot of problems for us and for everybody. If we were trying to design for that, walls would have had to get much thicker, so nice apartment layouts would have suffered. We'd have to try and figure out how to get all the piles over to the, get all the loads to the, into the piles at the wings, and it was just really turning into a disaster. So again, we looked at it from another perspective again and said, all right, well, really what we need to do is control differential settlements and control total settlements of the center of the tower. And we can't stuff any more piles into this thing. It's already 2.5 D on center. So of course the solution was to take the piles in the center of the tower deeper. So they ended up as 105 meters in total length, and we did that we wanted to stay above that competent sandstone at depth. We didn't want to have hard points at the center of the tower, so we chose 10 meters above that to give ourselves a nice cushion, and then we stepped it up at 2 intervals, 85 meters and 65 meters. And then we kept as many piles as we could at 45 meters. We still had this gravel zone that we didn't want to, if we didn't have to penetrate it, we didn't want to. So now things start looking a lot better. So on the left is our first cut again. That's the first wall loads takedown. And instead of 175 at the middle, we've got 107. And the first iteration, the wall loads did move around some still. We had about 50% increase on the end walls, but not nearly as bad as the first cut. And then our second iteration, the wall loads were essentially all less than 10%, and most of the time less than 5% change. So we felt like, all right, we've got it now. And then from that point, we sort of tweaked. We never changed the pile springs. We tweaked area springs. So at the end of the day, the geotechnical model and the safe model matched, and that's this plot here. So again, in plan, these are 100 millimeters at the center for us, 102 for TT. And of course, are we saying that it's going to settle this exactly 100 millimeters? I mean, of course not. But at least what we're saying is it's highly predictable. We both agree on how the foundation is going to behave. The pile loads similar, within 1 or 2 meganewtons at the most. So again, we're in agreement on how the raft is and the foundation is going to perform, and that made us both feel a lot better. So this is bearing pressures. Yellow is what, about 350 kPa, so very uniform. We've got a little bit increase at the edges, which is kind of matched what we saw in the wall loads moving around a little bit. The subgrade does take about 22% of the foundation load, which was useful not so much for geotechnical capacity, but for structural capacity of the piles. We really took advantage of that fact. And then the wall stresses, the similar model, again, wall stresses increased at the end walls by about 60%, but at least it wasn't more than a factor of 2 like we had been seeing before. And as Bob said, we're measuring structural performance of the tower as it's being constructed, and settlement points are being taken on the top of the raft. So this is at about 25% of the total gravity load on the raft. And that's at 10 millimeters at the bottom, not 100. So far we've got about 5 to 6 millimeters of movement for the center of the raft. And wing A is again about 5 to 6 millimeters, and the wings B and C look about the same. I think it's going to take off a little bit as the stress increase at that lower weaker layer, the poorly constituted sandstone starts increasing. I think it's going to increase some, but I think overall we've probably overpredict settlement probably by a factor of 2 is what my guess is. But again, I have Clyde Baker chirping in my ear every time, and he says, when you're doing something that nobody's done before, take baby steps. And tallest building in the world in a place that has no development at all and not really well understood geology, I think I'm okay that the foundation may be a little bit over-designed. So final thoughts. In our view, the geotechnical model governs the ground settlements. The iterative process not only necessary, but also gives insight into how the column and wall loads are going to move around as you converge. The stiffness of the superstructure and the stiffness of the foundation really have to be compatible, and that's what we saw in the beginning. Our foundation was too flexible, and the structure was really suffering. And in this case, the longer piles are not needed for geotechnical capacity. It's for settlement mitigation. And then the last one I will end with is, Bob, you were right, 25 millimeters from center to the edge is achievable and necessary. So